The sound source of a ship sonar system operates at a frequency of F ship. The speed of sound in water is denoted as V. The speed of sound in water is typically larger than in air. This is the nature of it because there's more particles closely concentrated together. Our goal is to find an expression for the difference in frequency. The difference in frequency here is the comparison of the high frequency minus the low frequency. This is between the directly radiated waves and the waves reflected from a whale traveling directly towards the ship. So the speed of the whale is denoted as V whale. This ship is at rest in water, so the water is very calm, that it appears stationary. Scenario 1, the listener is the whale approaching the ship, and the sound of the wave is produced by the ship here, so it's radiating from the ship. The equation that we have to consider is, of course, the Doppler equation, which is given by equation 1. Now, let us identify the nature or the behavior of each parameter. So, there are basically two parameters here that we have to consider: the speed of the whale and the speed of the ship. The whale is the listener, so it's in the numerator parameter. Now, since the whale is approaching the ship, the numerator should have an effect that it becomes larger. So that means we have to choose the positive sign here. For the ship, which acts as a source, is simply stationary, so this is just 0. So we arrive to equation 2. Now we then substitute some of the given parameters. For the V listener, that is referring to the whale. And of course, the Fs, the frequency of the source, is just the ship. So this is the frequency expression for the what the whale has received, as in equation 3. Now, let us consider scenario 2. The wave is reflected back to the ship. Okay, so the whale acts as a source while the ship acts as the listener. So it is now reversed. So let's look back at equation 1. Now, the listener is the ship, and we know the ship to be stationary, so this is 0. And for the denominator, the source, the whale, is approaching it, so that means the effect should be allows us, this parameter, to increase the frequency heard. So we choose the negative sign here, and we get equation 4. Now we then substitute the given parameters. Let us identify them. So F prime L, which is the frequency heard by the ship, is the one that is reflected. So we change the parameter here to F reflected. Fs prime here, the frequency of the source, the whale, as we know, is just simply the FL from scenario 1, okay, which you obtain and shown in equation 3. So if we substitute them, we get this expression here. Now this is simplified further by eliminating the v here, and we are left with equation 6. Now, the difference in frequency, as we mentioned earlier, is the difference between the directly radiated waves and the waves from the whale traveling. But note that there's a special case here because we wanted to take the difference from a high frequency minus the low frequency. Now, since the ship and the whale are basically approaching together, then the reflected waves would be higher. Hence, we have F reflected minus F ship. So, substituting the equations we obtained earlier, 6 and 7, we get this general expression. We simplify this further by extracting or factoring out the f ship, and we get a minus 1 here. We then obtain this expression by setting the denominator as v minus v well for both terms. So hence the numerator of the second term is v minus v well, because this one is just equal to 1. Simplifying further, we eliminate the v here, and we get this expression here. This is now the difference in the frequency for the directly radiated waves and the waves reflected from a whale traveling. And that's it.